Ever wondered about the physics of a duck on a water slide? Well, today we're going to work it out. Hi. So this video is going to be focused on working through a typical inclined plane physics problem, in particular, forces on inclined planes. And the subject of this problem is going to be a duck, a pretty hefty one at 2.5 kilograms, sliding down a water slide, as in the video you just watched. We're going to assume that this water slide, as most ideally are, is frictionless, and that it has an angle of inclination of 40 degrees relative to the horizontal. That means that on this image over here, the angle of inclination that we're looking at is this one right here. That's theta, and this theta we're going to call 40 degrees. So as with most force problems, the way you really want to start is by drawing a free body diagram. So over here, I'm going to first attach the one force that absolutely 100% of the time needs to be acting on an object, and that's the force due to gravity going straight down. Always. Okay? After that, well, this duck is on a surface, so it's going to have a normal force, or a perpendicular force, which acts perpendicular to the surface that the object is on. Like that. And believe it or not, that is a complete free body diagram, technically. So we need to start by laying out all of our ingredients, and the first step in that is usually just to find the force due to gravity. So part I over here, part 1, is to find Fg itself. That's a big question mark. So the force due to gravity is a fairly straightforward one. The equation we need there is Fg equals the mass of the duck, in this case, times the acceleration due to Earth's gravity. So the mass of the duck is 2.5 kilograms, we have that. And the acceleration due to Earth's gravity is always assumed. It's going to be 9.8, or if you were lazy like me, you can just use 10 meters per second squared to make things easier. That means that our force due to gravity overall is going to equal about 225 newtons for the sake of this problem. And that's part 1 done. The next thing we want to find is the normal force. In order to do this, we're going to start by looking at the usable information we now have. We have the force due to gravity as a value. The problem is, it's not really quite in the direction of the normal force yet. So your usual instinct is to split things into x and y, but in this case, we're actually going to do the opposite. We're going to split the force due to gravity into a parallel and perpendicular pair of components. So the force due to gravity, what I mean perpendicular is, gravity is not quite perpendicular or parallel, but as with any vector, it can be split into two smaller parts. And so if we split the force due to gravity into at least one component that's in the same line as the normal force, then if we're able to find this component of the larger gravity, then we can solve for the normal force. We're going to call this component of gravity Fg perpendicular. And so over here, our goal is to find the normal force. And in order to do that, we're going to always start with Newton's second law in the perpendicular direction. That's what the upside down T means. And this duck is sliding down the incline. It's sliding, not falling or flying. So perpendicular to the surface, we can assume that the duck isn't accelerating, that the forces there are going to add to 0. So then we're going to add up any and all perpendicular forces. So first, we've got normal force, which is going up away from the surface. And then added to that, we're assuming that gravity, part of its job is to pull the duck into the surface, downwards. So it's going to be minus Fg perpendicular. And those have to add to 0. Really quick then, that just means that the normal force is going to equal whatever this perpendicular component of gravity is. So then what does that perpendicular component equal? Well, over here, let's work out some trig really quick. So in doing this, we need to figure out what this angle is now. And one way we could think about it is, well, everything except for the force due to gravity has basically just been rotated by 40 degrees if we're looking at this incline here. So if the force due to gravity is where the Fg perpendicular is now, then believe it or not, using this triangle and this angle as a reference, this angle on this triangle that we're almost creating here is the exact same angle theta. Think of it as everything except gravity has just rotated by 40 degrees. And so just so we can complete the triangle here, let's go ahead and then say, well, the other component, we want a right triangle, so this other component is going to be down and to the right like this. So perpendicular to Fg perpendicular and it's going to be parallel to the surface. So if that's the case, then that means that FG perpendicular over here is going to be the adjacent side of this right triangle that we've almost created with respect to this angle here. So if we're treating the force due to gravity as the hypotenuse, then FG times cosine of theta will let us find that adjacent side. So over here then, it's going to be FG cosine theta. So FG we found to be 25 newtons times cosine of 40 degrees. And that should amount to about 19 newtons total. Now, part 3 is asking us to find the net force. We've already found that any and all forces in the perpendicular direction have to add to 0, that they all cancel each other out. So, assuming that the duck is moving, which we're being told it is, there still needs to be some kind of force that's like causing this duck to accelerate down the incline or the water slide. In this case, there's one direction that we haven't really accounted for yet, and that's the parallel direction. So if we're supposing that this duck's motion is parallel to the surface like that, then we want to use the sum of the forces in the parallel direction with Newton's second law, so that these forces added together equal the duck's mass times its acceleration that we're trying to find. And since we're really just looking for the net force here, we're just going to add the forces and see what happens. So overall, gravity has another part to it. So if we complete our right triangle by adding a component of gravity that's parallel to the surface now, we can call that component FG parallel. And the job of this part of gravity is simply to pull the duck down the incline, which if you're ever on an inclined plane, you typically feel that part of gravity. It's what's responsible for making things slide. So then, assuming there's no friction or any other forces that could be acting in that direction, then it's really just FG parallel that's going to equal whatever we want. So up here then, let's go ahead and find that, and we're looking at the opposite side with respect to the angle, so FG parallel. And so that's going to equal FG sine of theta, assuming again that gravity is the hypotenuse there. So then over here, let's just say 25 newtons, again, for the overall force due to gravity, times sine of 40 degrees. And that should equal about 16 newtons total. And that is our net force, believe it or not. So next, we need to find the acceleration of the duck. So again, we're going to start with Newton's second law in the parallel direction here. And we have the mass, we have the net force now, it was 16 newtons. So let's just make some quick substitutions. The net force in the parallel direction we found to be 16 newtons. And that's going to equal 2.5 kilograms times the acceleration in the parallel direction. So then the acceleration of the duck without any friction is going to equal about 6.4 meters per second squared. That duck is zooming. All right, now the last part here is, assuming that the duck and slide did have a friction coefficient of about 0.1. So now we're assuming that it is frictionless. We want to see what the new acceleration of that system would be. So in this case, friction is a contrarian. So really its job is to oppose the direction of motion. So that's going to apply a force this way, parallel to the surface. And so over here, our first job then is, well, we need to figure out what friction is. So the force due to friction is just the coefficient, mu, times the normal force, which we solved for earlier. So it'll be mu times Fn. And if mu is 0.1 and the normal force, by comparison, was found to be 19 newtons, then simply enough, our friction force is just going to be 1.9 newtons. So then again, friction is a parallel force. So like last time, we need to add up our parallel forces. So over here, we're going to find the sum of the parallel forces, which is now going to be the force due to gravity in the parallel direction, bringing it down the incline, which we'll consider to be the positive direction, plus a negative friction force going against it. And so if we add those together, it's going to be 16 newtons pulling us down minus 1.9 newtons pulling us up. And so in the end, we can expect a total net force of about 14.1 newtons. And so to finish it off, to find our new acceleration, well, we can say that the acceleration is really just going to be the sum of the forces in the parallel direction divided by whatever the mass of the object is. So if our net force in the parallel direction was 14.1 newtons, and we're dividing that by the duck's mass, 2.5 kilograms, then we can expect our new acceleration to be about 5.6 meters per second squared, which is to be expected because friction does slow things down. So after all of that, this is usually all of the things that you would expect to see in an inclined plane sort of problem, other than maybe adding extra forces involved besides friction. So I hope this video helped. Don't forget to like and subscribe, and I will catch you on the next one. Peace.